Hi everyone. Today we are learning about rate and reaction stoichiometry. We've touched on this before the other day, but we'll just go more in depth with it now. And this is lesson 3.4. Okay. Now, just to review here, we've said this before that rate is your change in whatever it is you're looking at, so some observable change, the change in x divided by the change in time. So this would be slope, right? So the rate, it's important to note, is going to be positive for the formation of a product and negative for the consumption of a product here. And so just make sure you're paying attention to that little negative sign there. And we can see that in our graphs here, because we know that rate is defined as slope. And if we look at the reagents, these are the reactants, okay? It's just another word for that. So if we look at the reactants here, these are getting used up, right? The reactants. So this is the consumption. And if we look here, if we were to find the slope for various points here or any instantaneous rates, they would all be negative slopes, right? Meaning the rate is negative. And then conversely, of course, the products, this is this curve here, moving up that way, we know that that would have a positive slope. It's upwards and to the right. So the rate is going to be positive for that one. Now, we're going to take a look at this reaction here and just sort of go through some vocabulary here. I'm just going to draw these out so we can sort of clearly see it here. So if we have N2, and then let's use blue here, and then we've got 3 of H2, so this would be 2 hydrogen. That was not very good. You'd think I would be better at using a stylus by this time. You would think that. Okay. So there we've got our 3 hydrogen molecules, and what they make here is 2 NH3s. So this is our ammonium, so I'm going to have 2 of the ammoniums, hold on, and these are surrounded by 3 hydrogen atoms. Okay, so now we can clearly see the molecules, right? So we've got 1 molecule of nitrogen, 3 molecules of hydrogen gas, and 2 molecules of your ammonium. Okay, so what we can say then is that for every nitrogen gas molecule, so for every 1 here, there's a 1 there, remember, 3 H2 molecules need to be consumed. So the ratio there is 1 to 3. This means that the rate of consumption of H2 has to be 3 times the rate of consumption of N2. Because remember, the rate that N2 is being consumed and H2 is being consumed is the same, but I've got 3 times as many hydrogen molecules there. So the rate has to be 3 times faster. I can also say for every molecule of N2 that is consumed, the rate of production of the NH3 molecules is doubled, and I know that because of the 2. And I can see that for every 1 nitrogen molecule that is consumed, 2 ammonium molecules are produced. So the rate has to be twice that as fast as the nitrogen. So sometimes people get caught up in the language here, so you just got to be careful. So again, we can say the rate, no, this is just flipping your thinking here. So we can say the rate of consumption of N2 is 1/3 the rate of consumption of H2. So we can either say that the hydrogen is 3 times that of N2, or we could say that N2 is 1/3 that of the H2. So those mathematically are going to be the same things there. And the rate of consumption of H2 is half the rate of production of NH3. Hold on here, the rate of consumption of N2 is 1/3 the rate of consumption of H2, right, and 1/3 the rate of production of NH3. So this is just getting used to the language here. We could also say that N2 is consumed at 1/3 the rate of H2, and 1/2 the rate that NH3 is produced. Okay, so just depending on what you're looking at there. Hold on, sorry. Yeah, so different language there. Okay, now we can use these mole ratios here. So if the rate of one of the species is known, the rates of the other species can be determined by the reaction stoichiometry. So the mole ratio comes into play here. So remember, we've got our N2 plus 3H2 goes to 2NH3. And so we can build this expression here, which is called the rate expression. And I'm just going to rewrite it underneath here because I want you to pay attention to the fractions here. So the rate is going to be equal to, now remember, if it's being consumed, you're going to have a negative rate. So negative delta, we use square brackets to show concentration, over delta T, equals, and then we have 1/3, so negative 1/3, and then delta H2 over delta T equals, and now we have to go positive because the NH3 is being produced, right? So 1/2 delta NH3 over delta T. So as you can see, these numbers here, and there'd be a 1 there really, right, come from here, okay? So the balanced equation is going to be, is going to tell you what the rate expression is, because they're going to, these things are going, the rates will be dependent upon the mole ratio here. Okay. Now, problem. So we're just going to work through this. And this looks like what we did the other day, actually. I think it was in the first lesson, actually. So the problem, if hydrogen gas reacts at a rate of 1.5 moles per liter times second, what is the rate of formation of ammonia? So you have, first of all, let's go ahead and balance this here. So it's telling you that the rate of H2 is 1.5, moles per liter times second, and you are asked to find the rate of the NH3. So we can do this just by using the mole ratios, and I would set it up using dimensional analysis. You don't have to, of course. You can use whatever you want here, but I'm going to say rate is equal to 1.5, and here I'm going to say, moles per liter times second, and then it's H2 here, so H2. And now I'm just going to multiply by the ratio, so the moles of H2 is going to be on the bottom, and moles of NH3 are going to be on top, and the mole ratio between them is 2/3. So this would mean that the rate of, oh sorry, I should have had here, of NH3 is going to be 2/3 that of the H2. And so I can work that out, and I end up with 1.0 moles per liter times second. And that's the unit here, NH3, for this particular one. So we just used our mole ratio here to show and to convert between the rates. Okay. So write the rate expression for the reaction 2A plus B goes to 3C, or yields 3C. So when writing rate expressions, you just look at the balanced equation. Now don't forget your negatives and positives though. So remember, the reactants are going to end up having negative rates because they're being consumed, and the products are being produced, therefore they'll have a positive rate. So I'm going to have negative 1/2 for the first, so I have to pay attention to that. And then it's going to be times delta A over delta T equals, again, negative B, there's a 1 there, so I don't need to write anything here, delta B over delta T. And now I look here, and this is going to be positive 1/3 delta C over delta T. So that would be your rate expression here. Make sure you don't forget the positives and negatives. You will be asked to do this, so it's pretty straightforward, so make sure you understand how to do that. Next part, we're going to look at the stoichiometry here. So if A is being consumed at a rate, and so the rate's given there as negative 3.2 times 10 to the negative 2 moles per liter times second, what is the rate of production of B? So we're going to use our dimensional analysis. So the rate, sorry. So the rate of B, the production of B, is going to be equal to, and here I'm going to write 3.2 times 10 to the negative 2 moles per liter times second of A. Now I'm just going to multiply it by the mole ratio here. So moles of A goes to the bottom. Remember, diagonal units are always the same. Moles of B go on top. So I'm just multiplying this by the mole ratio to factor that in. And so moles of A, I'm going to use the balanced equation to get those coefficients. So I've got 2 of A, 1 of B. So then I'm just going to divide this 1 by 2, and you end up getting 0.016, and it's going to be moles of B. Actually, sorry, I wrote this. Oh, crap. Yeah, moles of B per liters times second. Sorry, I think I shouldn't have had the... Yeah, no, I did it right there. Anyways, sorry. So 0.016 moles of B per liter times second. You could also write it then, I guess, as 0.16 and then the concentration of B per second. That would also work if you'd rather write it like that. But it's up to you. Mathematically, they both mean the same thing. So take a look at that. These are all they're pretty much the same thing over and over again. You're just looking at the balanced equation and using that information, multiplying by the mole ratio. So you can go ahead and try exercise 2. You have the answer key. It's already posted for you. So you can take a look at that there and make sure you're asking questions if you have them. Thanks, everyone.